This presentation is about application of change of variable to observability method. The outlines are introduction and description of the methodology. Triangular elements are one of the best elements that can be used for modeling of irregular boundaries and have been used extensively for continuum stress analysis. As shown in the figure, quadratically interpolated triangular element has 6 nodes, 3 at each vertices and 3 nodes at midpoint of each side. This element is very useful in modeling of geometries that the use of 8-noded quadrilateral element leads to undesirable deformation and makes some problem in Jacobian mapping. For analysis and design of structures, we have to use the general formula, which is F is equal K times D. For 2D elements, we have 2 degrees of freedom on each node since we have only vertical and horizontal displacement. Therefore, size of a stiffness matrix is 2 times n by 2 times n. Matrix K contains mechanical parameters of the structure such as Young modulus, thickness, and Poisson ratio. And after that, vector delta contains vertical and horizontal displacement. And for other side of the equation, which is matrix of forces, contains vertical and horizontal forces. For explaining the advantages of change of variable to observability method, we selected the thin plate, which is subjected to uniformly distributed load with different mechanical properties for each element. In the below figure, we have equilibrium equation for this small structure. Here is our main equation. Because of the complexity of the matrix, I just derive elements type that may appear in the stiffness matrix. Analysis of the equation shows that the Poisson ratio appears in the numerator of the fraction. Its location complicates significantly its estimation. In fact, the resulting system cannot easily be solved with observability techniques. And from the other hand, when we transfer the unknowns from stiffness matrix to the vector of delta, they are getting multiplied by our deflection, which leads to have nonlinear equation. To solve this problem, a change of variable proposed. This change simplifies the mathematical resolution of the system and enables the application of observability technique as the new unknown parameters appear uniquely in the matrix. Therefore, first the denominator of the fraction are decomposed, and after that, by assuming C is equal to nu, Q is 1 over nu plus 1, and M is equal 1 over 2 times nu minus 1, the elements of the stiffness matrix will be changed to these 4 types. To have better recognition of this change of variables to our system of equation, this slide shows the first and last columns of stiffness matrix, which are related to H1 and V9.